Let's jump to you.
Yeah, so we're going to continue our series on exoplanet detection. And if for those of you who've been following us, by the time we finish this, you will be exoplanet experts. So I'm sure we'll have a certificate or something for you, and you can present it to your graduate program. So we've talked about the first detection, where the pulsar that the planet was orbiting, where its timing was thrown off a bit by the orbiting planet. We've talked about radial detection method, where the star is pulled towards us and away from us similarly, but we detect that through the change in the frequency, through the Doppler effect, the change in the frequency of its spectrum. And today we're going to talk about the holy grail of exoplanet detection, and that is the transit detection method. This is a method that has produced the most identifications of exoplanets to date. That may change with JWST and its ability to actually image planets. So let me share my screen a little bit here.
Just while you're doing that, Lou, we have a question in the comments, I think, Rachel?
Yes.
Yeah, I've just popped it in. He's asking, he's bought a Celestron Skymaster 20 by 80 binoculars. Is it good for astronomy? What can he see with it? Can he find any deep sky messy objects or planets?
They're a little bit heavy, but they're fantastic if you have a nice chair to sit back in. And I especially love looking all around Sagittarius in the summertime, because you can see the lagoon with the binoculars. You can see some of the clusters, but you can especially see kind of the arm of the Milky Way. And then look for Andromeda, star hop to Andromeda with your binoculars. And as soon as you figure out how to do that, you're going to fall in love with looking at Andromeda with binoculars.
Yeah. Binoculars are excellent for viewing. If they are too heavy and you find that they are a bit too much to handle, there is a device called a parallelogram, I believe it's called, which you can set up beside your deck chair. And once you've set up the angle, you can move them anywhere and they will stay on that object. So you don't have to hold them so much. But also, you will be able to see messier objects, and you will be able to see the planets.
There we are then.
And the moons of Jupiter, which are fantastic to see with binoculars, and even just a basic tripod will do the trick.
Yeah.
And Titan, let's not forget Titan.
Oh, of course.
Yes.
Right, back to Lou.
Yes.
Okay. All right, so sorry for having that animation up while you all are talking. The transit detection method takes advantage of the fact that for some planetary systems, the planet moves in front of the star as we see it from Earth. Its orbit is kind of planar with our view, and therefore blocks out a little bit of the sun, of that star's light. And so I can show that here. Do that. There we go. There we go. So this is a graphic showing a planet moving in front of its star in its orbit. And you can see the light from the star dimming and then recovering. And you can actually tell quite a bit about the planet and the star from this kind of back and forth. First of all, obviously, you can tell what the period of rotation of the planet is. If you look at the angle with which the light is diminished and then recovering, that angle, you can tell a little bit about the atmosphere of the planet. Right? A planet with no atmosphere would kind of cut the light off much more cleanly. If you know something about the star, from its spectrum and its size, you can tell what the inclination of the orbit of the planet is, and also the size of the planet. So you can get quite a bit of information out of this transit detection method. The problem is that it only works well for, again, planets that orbit within the plane of, or close to the plane of our line of sight. And so this method actually favors very large planets that orbit very close to their star, because we're more likely to see some of the star's light obscured from those kinds of planets. Let's see if we can go forward here. Here's another example of using the transit detection method to detect planets around another star. In this case, we have, I think, 6 planets orbiting this star. And you can see the periodic data dropouts, the diminishing of light periodically from each of these planets. And so by observing this, you can kind of tease that apart and tell that it's a multi-planetary system, and do the other analysis that we just talked about to try to define the nature of the planets and their orbits. So this is a very powerful method of detection. And one of the reasons we have made so many discoveries about this is we not only have ground-based telescopes looking for transiting planets. We have Kepler spacecraft. We have the TESS spacecraft. And certainly we're going to discover other planets with JWST, probably through imaging as well. So go to the next slide. Here's I think I brought this slide up a couple of weeks ago. Here's a kind of an accounting of the number of planets that we've discovered from each of these different kinds of exoplanet detection methods. And we're going to go over a lot of these in this series. So you can see in the red down here, we have the radial velocity detection method. It's a lot of detections. And we're sitting right on top of it in the green is the transit detection method. Most of the stars, most of the exoplanets that have been discovered to date have been discovered by the transit detection method. So I'm just going to end here with once again with the website for the NASA Exoplanet Archive. If you want to know how many planets have been detected, what they're like, what stars are orbiting, where they are, anything you want to know, the NASA Exoplanet Archive has lots of great information, and you can check this out. So that's what I have for you today.